Imagine waking up tomorrow and every single map on Earth is gone. No GPS, no Google Earth, no atlas hiding in your bookshelf, not even that crumpled road map in your car's glove box. Just gone. And now, you have to get to a town 2 days away on foot. There are no signs, no friendly this way to the bakery arrows. Just you, the open land, and a vague feeling that the sun probably rises in the east. That's the world most humans lived in for most of history. Sure, people traveled, they traded, they visited other villages, but if you were going somewhere you'd never been, you either had to find someone who knew the way, or guessing usually ended badly. People got lost, ran out of food, ran into unfriendly neighbors, or discovered they'd walked 3 days in the wrong direction, and now they were out of shoes. And asking for directions wasn't exactly like today. If you stopped in a village in, say, 1200 BCE and asked, "Hey, how do I get to Rivertown?" the answer might be, you walk toward the mountains until the land feels different. Then you follow the smell of the big marsh. If you pass the giant rock shaped like a goat, you've gone too far. Helpful. This was the reality. The world was a messy, unmeasured place. People didn't think in precise distances like it's 42 kilometers from here to there. They thought in terms of landmarks, weather patterns, and how many days your cousin took to make the trip last time he tried it. Without maps, the shape of the world was a mystery. You could know your valley perfectly, every bend in the river, and every tree big enough to nap under. But the next valley over, that could be full of gold, or dragons, or both, and you wouldn't know until you went there. Here's the thing. Humans have always been curious. We don't like not knowing. When we can't see the bigger picture, we imagine it. And for most of history, those imaginations were wildly creative. Some cultures pictured the world as a flat disk floating on water. Others imagined it sitting on the back of a giant turtle. Some thought it was an infinite plain with mountains holding up the sky like pillars. But curiosity leads to questions. Questions lead to experiments. And experiments, well, they lead to math. Before maps, people still measured things. Hunters counted steps between landmarks so they could find their way back. Traders measured how many days it took to reach a market, and how much food they'd need. Farmers measured plots of land, because if you plant your crops in your neighbor's field, you suddenly have a neighbor with a very sharp stick. It's in these everyday problems that the seeds of map-making were planted. If you can measure a thing, you can describe it. If you can describe it, you can share it. And once you can share it, other people can use that knowledge to go places you've never been. Of course, the first attempts at maps were more like memory aids. A trader might scratch lines in the dirt to show where rivers were, or carve a rough coastline into a piece of wood. Think of them like prehistoric napkin doodles. Not pretty, not to scale, but better than nothing. Now, picture this. You're part of a caravan traveling through the desert. You have one of these maps carved into wood, showing the path from Oasis A to Oasis B. Problem is, nobody bothered to mark the distance. So you walk and walk, your camels are tired, you're thirsty, and you start wondering if the guy who made this map was just drawing random squiggles. Eventually you find the oasis, but you've been grumpy for 3 days, and you're never trusting that map maker again. This is why accuracy matters. And accuracy is where math starts to sneak in. To make a real map, you need to know distances. You need to know directions. You need to be able to record them in a way that someone else can follow without you standing there pointing. And that's not easy without compasses, protractors, or laser rangefinders. But humans are stubborn. Give us a problem and a bit of free time, and we'll try to solve it. So in those early mapless centuries, we start seeing the first glimmers of measuring culture. People used sticks, ropes, and even their own bodies to measure things. A step might be a unit. So could the length of your arm or the distance from your nose to your outstretched fingertips? Sure, it wasn't standard. My arm is not your arm, but it worked locally. Slowly, patterns emerged. People realized you could pace out a distance and keep track by counting. You could use the sun to figure out east and west. You could note that certain landmarks always lined up with certain stars at night. And from these little tricks, entire networks of travel knowledge started forming. Think of it as the world's earliest GPS, except the satellites were goats, oddly shaped rocks, and that tree that looks like my aunt's hat. And here's where the story gets fun. These rough systems of measurement didn't just help travelers, they changed how people thought about the world. When you can say it's 3 days' walk to the next village, you start to picture your home in relation to that village. And when that village knows about another one 5 days beyond it, suddenly you're picturing a bigger world. Piece by piece, these mental maps grew until someone somewhere thought we should draw this down properly. Of course, properly was a relative term. The first true maps we have from history are hilariously bad by modern standards. Some are just circles with a river through them. Some put mythical creatures in the corners to warn travelers not to go there, and some are so wildly inaccurate, you have to wonder if the mapmaker ever left their house. But they were a start. A visible, shareable start. And once humans start doing something, they get competitive. If one village has a map, another village wants a better one. And that push for better maps, that's where the measuring really takes off. We'll get to those maps soon. But for now, just sit with the idea that for tens of thousands of years, humans roamed this planet without knowing its shape, its size, or where they were on it. They lived in a giant mystery, filling in the blanks with stories and guesses. And yet, they managed, they explored, they survived, and eventually, they started to measure. Because deep down, we are all a little obsessed with knowing where we are and what's around the corner. And in that obsession lies the very first spark of the mapmakers, who would, one day, measure the world. Before there were compasses, before there were globes, before anyone even thought of drawing the earth as a circle or a sphere or a turtle's back, there was walking, and counting. That's it. If you wanted to measure how far away something was, you counted how many steps it took to get there. That's the earliest distance measuring tool humans had, our own 2 feet. And sure, it sounds simple, but it comes with a small problem. Everyone's steps are different. If you've ever walked with someone who takes giant strides, you know the frustration. You're taking 3 little steps for every one of theirs. Now imagine trying to map an entire valley with that problem. In some places, people tried to solve this by picking one person as the official step measurer. Usually it was someone with a steady pace, not too big, not too small, kind of like a human metronome. And that person's step length became the unit of measurement. But that meant if your village's measurer sprained an ankle or worse, died, your whole system was ruined. Suddenly a day's walk might be a lot shorter or longer than you thought. So people got creative. They started using objects to measure. The most basic was the stick. It sounds primitive, but a stick was genius. You could cut it to a set length, carry it with you, and lay it down end to end on the ground to measure distances. This worked great, as long as your stick didn't break, warp in the rain, or mysteriously shrink when your little brother decided it made a better fear. The Egyptians were especially famous for their ropes. They had rope stretchers, actual teams of people whose job was to measure land by stretching ropes between points. These ropes were knotted at equal intervals, which made it easy to measure the same length over and over. It wasn't perfect. Ropes stretch after all, but it was consistent enough to keep fields and property lines in order. And in a society that taxed people based on how much land they had, getting those measurements right really mattered. Now, these early measuring methods weren't just about curiosity, they were survival tools. Traders needed to know how far they could go before their camels collapsed from exhaustion. Farmers needed to know how much land they had to plant and how much seed they'd need for it. Even hunters needed to measure, not with numbers but with instincts, how far they could chase an animal before they'd be too tired to drag it home. And then there were travelers. Imagine you're heading to a market in another town. You've been there once before, so you know it's about 5,000 steps from the river to the crossroads, and then maybe 2,000 steps more to the market square. That's how you think about it. In steps. No one says 7 kilometers. That's a foreign concept. It's half a day if you don't stop to talk to the shepherds. Of course, this system had flaws. Let's say you're counting your steps, but halfway through you get distracted because you saw a goat doing something funny. You lose count. Now what? Start over. Guess. This is how you end up with travel times that are hilariously wrong. Over time, some people tried to make the counting easier. They used pebbles or beads, moving one from one pocket to another every 100 steps. Others sang little songs that matched their walking pace so they could keep a rhythm and estimate distance. That's right. The first pedometers were basically music and pockets. But humans being humans, we didn't just stop at counting steps. We started comparing distances. The lake is about the same distance from here as the mountain is from the forest. This might sound obvious, but it's the birth of scaling. The idea that you can represent different distances in relation to each other. And scaling is the foundation of mapping. Let's go back to those sticks for a moment. If you have a stick of known length, you can start to measure things that aren't just in a straight line. You can measure the length of a building, the width of a river, or the distance between two trees. And if you're clever enough, you can start using geometry, even if you don't know it's called geometry yet. You might notice that if you measure the same distance twice at different angles, you can figure out where the two measurements meet. That's the baby form of triangulation, one of the most important map-making tools in history. But back in these early days, it was more like, if we walk this far north and then this far east, we end up here. People didn't have compasses, so north and east were more like toward the big hill and toward the sunrise. Directions were anchored to the natural world, mountains, rivers, stars. Speaking of stars, this is where measuring got really interesting. Some ancient travelers noticed that certain stars rose and set at predictable points on the horizon. If you paid attention, you could use them to figure out direction. Over long journeys, you might notice that the position of certain stars changed slightly depending on where you were. You wouldn't know it yet, but you were actually detecting the curvature of the Earth. And yes, people were picking up on this long before anyone proved the Earth was round. Still, most travel was local. Measurement systems stayed small and personal. Your unit of distance was whatever made sense to your community. That's why when ancient civilizations started to trade with each other, they had to invent conversion systems. It's like if you showed up to a race expecting to run 100 meters, and someone else told you, oh, we measure that in elephant lengths here. The shift from these step and stick systems to actual map making took thousands of years. But the groundwork was here. People were learning that you could represent the physical world in consistent, repeatable units. That idea that the world could be measured is what gave birth to everything from agriculture to architecture to navigation. And let's not forget the human side of it. Measuring wasn't just about math. It was about stories. It's 10 sticks from the old oak to the riverbank. Could be both a fact and part of a family memory. Distances became part of the way people described their world, how they told each other where to go, and how they passed knowledge down. When you think about it, those early step counters and rope stretchers weren't just measuring space. They were building the mental maps that would later become real maps. And all of it started with something as simple as putting one foot in front of the other and keeping track. The irony is, today we carry tiny computers in our pockets that can tell us exactly how far we've gone, down to the meter, yet somehow we still get lost. Maybe it's because we've lost the habit of paying attention to the land around us. Those ancient traders and travelers, they noticed everything. The slope of the ground, the smell of the air, the way a certain tree leaned. To them, the world itself was the map, and measuring was just a way of reading it. It's almost poetic. Measuring the world didn't start with grand expeditions or brilliant scientists. It started with people walking, counting and trying to make sense of their surroundings. And from that humble beginning, The journey to map the entire planet had begun. Picture the Nile at sunrise. The river is calm, wide, and pretending to be your friend. Then it isn't. It rises. It spills over its banks. It wipes out the neat little lines that say, "This is my field, not yours, Hassan." The flood brings life. It also erases property lines like a bored cat erases a sandcastle. When the water goes down, nobody knows where anything ends or begins. Welcome to ancient Egypt's annual math problem. This is where the rope stretchers walk in. They are surveyors. In Greek, later they get a fancy name, harpdanapte, which basically means rope people. It sounds funny, but their job is serious. They keep peace between neighbors. They keep tax collectors happy, and they give us one of the earliest examples of practical geometry. What do they carry? Ropes, of course, but not just any ropes. These ropes have knots at regular intervals. Think 12 equally spaced knots, making 11 equal segments. It's a portable measuring tape that works in the heat, in the mud, and in the middle of a shouting match about where Uncle Tetty's fig tree used to be. A rope with knots is easy to lay out, easy to count, easy to pick up, and most importantly, easy to repeat. Repeatability is the secret source of measurement. The rope stretchers also carry poles and plumb lines. A plumb line is a string with a weight at the end. Gravity pulls it straight down. With that, you know what straight means, even if your cousin insists the ground is basically flat. They use simple sighting tools to look along a line, mark a point, and carry that point forward. In other words, they turn a messy floodplain into a grid you can argue about with numbers. Let's talk units. Egyptians like body-based units. The cubit is the rock star. From elbow to fingertip. There's a royal cubit and a common cubit, because of course there is. The royal one is longer, because pharaohs like upgrades. They also use the palm and the digit. Palm is 4 digits. 5 palms make a span. There are neat wooden cubit rods with carved marks. You can hold one in your hand and say, "Look, this is a thing, not a vibe." Your neighbor can argue with your jokes, but not with your cubit rod. Now for the fun bit. Right angles. How do you make a right angle in a field with no metal square and no app that says 90 degrees achieved? You use the 12-knot rope. You make a triangle with sides 3, 4, and 5 units. Lay out 3 knots on one side, 4 on another, 5 for the long side. Pull it tight. Boom. You get a right angle. It's practical Pythagoras. Before Pythagoras, workers can build straight walls and square corners using only a rope and common sense. Is it magic? No. It is number magic, which is better. The rope stretchers measure fields after the flood. They walk the boundaries, lay ropes, mark corners with stones or wooden stakes. They write things down on papyrus. A rectangle here, a trapezoid there, a weird shape shaped like a loaf of bread, because real land is never tidy. Then comes the math. How big is this field? The area decides tax. Grain in, grain out. Numbers mean bread. Did they have formulas? Yes. We can peek at the rhymed mathematical papyrus, a kind of student workbook from around 1550 BCE. It includes methods to find areas of rectangles, triangles, even circles. Their circle method is charming. They take the diameter, subtract 1/9, then square that. It gives an approximation of pi about 3.16. Not exact, but good enough to build things that last thousands of years. If your neighbor complains, you can say, "Friend, this pyramid is still here, your argument is not." Back to the flood. The Nile flood level changes year to year. Sometimes it is too low and the crops suffer. Sometimes it is too high and the frogs consider buying boats. Egypt tracks the height using nilometers, stone staircases and markings inside wells or along the river. Priests read the water like accountants read spreadsheets. High flood, big harvest, higher taxes. Low flood, sad harvest, careful taxes. The rope stretchers and the nilometer readers form a quiet team. One group measures height of water, the other measures shape of land. Together they measure a civilization. You can imagine the social life of a rope stretcher. They walk into a village after the water retreats. Half the people wave, the other half scowl because taxes are coming. A farmer says, "My field was bigger last year." Another says, "His field grew legs and walked into mine." The rope team smiles, drops the rope, anchors a corner, pulls it tight, counts knots and marks. They pace the sides, use the plumb line to keep straight, and call out numbers. The scribes write, numbers calm tempers at least for a while. Math is not only truth, it is therapy. We should talk about how this measuring builds maps. At first it is local, a field plan, a sketch of the village, a drawing that shows the canal, the temple, the clusters of palms. Over time these small maps join, tax records become like tiles of a mosaic. Put enough tiles together, and you start to see a region. Put more, and you see the kingdom. It is not a world map yet, but it is a way of thinking that says the world can be drawn because the world can be measured. There is also a quiet elegance in their tools. A rope, a rod, a plumb line, no fancy gear. The insight is not the tool, it is the method. Fix a baseline, set a right angle, measure along that line, close the shape, check your work by returning to the starting point. If it doesn't close, you made a mistake or you stepped in soft mud. Do it again. Ancient quality control. Here's a scene. Two surveyors stand in the sun. One holds the end of the rope on a marker stone. The other walks away counting knots. A boy holds the plumb line. A scribe shades a papyrus with his hand and writes. The wind moves the reeds. A crocodile watches in boredom. The numbers are small. The moment is small. But piece by piece, this is how a civilization becomes precise. Of course, there are jokes. A farmer says, "The rope shrank this year." The surveyor smiles and says, "The rope is loyal to the pharaoh, not to your wheat." Another farmer says, "My cousin's field is a triangle. Triangles pay less tax." The rope team says, "Congratulations on your new triangle. We will measure it with 3 sides and you will still pay. Humor keeps tempers cool and numbers do not." The math sneaks into building too. You want a straight canal? Use the rope to set a line. You want a square courtyard? Use the 3-4-5 triangle. You want a wall that stands? Use the plumb line. Geometry stops being an idea and becomes a habit. Once you've seen a straight line, you start seeing crooked lines everywhere. That's the beginning of engineering taste. There is something tender in all this. The flood wipes away borders. The rope puts them back. Nature erases. Humans redraw. Every year is a reminder that we live between chaos and order, and a knot in a rope can pull us a little toward order. You can feel the calm that comes when a corner is set, when a line is true, when a figure is closed. It is the calm of we know where we are again. And then, the bigger thought. If rope and sight and counting can tame a field, maybe rope and sight and counting can tame a kingdom, maybe even the earth. The rope stretchers do not say this out loud. They are busy keeping neighbors from arguing about a fig tree, but their method plants the idea that measurement scales. Today a field, tomorrow a road. One day, a meridian drawn across continents. So when we think of ancient Egypt, we see pyramids, gods, paint that still glows after millennia. But we should also see a quiet crew with a knotted rope walking the edges of a muddy field, founding the culture of measurement. Without them, there is no property, no tax, no building plan, no map. With them, there is a way to turn the world into lines and numbers that other people can use. That is why the rope stretchers matter. They show us that geometry starts on the ground, with bare feet and patience. They show us that math lives in tools as much as in minds. They show us that a right angle can be a kind of peace treaty, and in the long, long story of how we measured the world, they are the first chorus, singing in knots and cubits and sunlight, before the paper map, before the leather scroll, before even the papyrus of Egypt. There was clay, wet, squishy, sun-baked clay. If you lived in Mesopotamia around 200 and 500 BCE, clay was your notebook, your filing system, and if you were a little careless, your lunch plate. It was durable, cheap, and if you messed up, you just squished it flat and started over. And one day, somebody decided to put a map on it. The Babylonians were not just farmers and builders, they were record keepers. They loved writing things down. They had cuneiform, a writing system of wedge-shaped marks pressed into clay tablets with a reed stylus. They used it to track grain, debts, laws, star positions, and in a moment of inspired practicality, they also used it to track where things were in the world. Now, don't expect a Babylonian map to look like anything you'd see in an atlas today. The most famous surviving one is about the size of your hand. It's a little roundish tablet showing the world as they knew it. Babylon in the center, a few surrounding regions, and a river running across it. Around the outside is what they called the Bitter River, the ocean. Beyond that, mysterious triangles marking distant, possibly mythical lands. Think of it as half geography, half fantasy novel. What's amazing is that this was one of the first times humans tried to represent their environment from a top-down view. Most people in history saw the world from the ground. The Babylonians decided to draw it from above. It's a mental leap, going from I walk along the river to let's show the river as a line on a flat surface. That leap is the seed of cartography. How did they know what to draw? Mostly from trade and travel. Babylon was a hub, connected by rivers and roads to other cities and empires. Merchants came back with stories, some true, some wildly exaggerated. The mountains to the north are full of silver, might be true. The mountains to the north are guarded by scorpion men, is probably not. But both kinds of stories made it onto the mental maps people carried in their heads. The clay tablets were a way to freeze those mental maps in a form that could outlive the storyteller, and clay was perfect for that. A papyrus map could rot, a leather one could mold, but clay once baked could last thousands of years, which is why we can still look at them today, turning them over in museums and imagining the hands that made them. The style of these maps was simple: lines for rivers, dots or little shapes for cities, wedges of text explaining what's where. No scale bars, no compass roses, no "you are here" arrows. The Babylonians weren't interested in precise distances. Their maps were more about relationships. This city is next to this river. This land is beyond this mountain. It was a diagram of connections rather than a precise blueprint. And yet, math was there. The Babylonians were excellent mathematicians. They worked in base 60, which is why we still have 60 minutes in an hour and 360 degrees in a circle. This number system made it easy for them to divide things into neat fractions, which was handy for trade, astronomy, and yes, even mapping. When they said a road took a certain number of baru to travel, they meant a standardized time-distance unit, how far you could go in about 2 hours of walking. That's not GPS, but it's not bad either. Their astronomy also influenced their mapping. Babylonians charted the heavens with remarkable precision. They tracked the movement of planets, predicted eclipses, and recorded star positions. Knowing where stars rose and set helped them orient themselves on the ground. If you knew the star you called the true shepherd rose over a certain mountain range, you could use it as a cosmic signpost. And here's the charming part. Their maps didn't separate the real from the mythical. To them, the distant edges of the world might well have been inhabited by strange creatures or gods. These were not mistakes. They were reflections of how they understood reality. A blend of observation, hearsay, and imagination. Our modern maps might not have scorpion men on them, but we still fill our mental maps with things we've only half confirmed. The difference is that now we call it rumor or urban legend instead of cartography. Let's imagine the making of one of these clay maps. You've got a lump of clay the size of a small loaf of bread. You flatten it into a tablet. With a reed stylus, you press in a circle for Babylon. You draw a couple of lines for the Euphrates and Tigris rivers. You mark nearby towns with little wedges. Around the edge you press a wavy line for the ocean. Then for fun you add some triangles at the rim, the outer regions. Maybe you label them Land of Darkness, or Place Where the Sun is Hidden. You bake the tablet, and now you have something that can sit on a shelf, be copied or be handed to someone traveling far away. These clay maps were also political. Putting Babylon in the center wasn't just geography, it was propaganda. We are the center of the world, the map says. It's a message to anyone who sees it. The known world radiates from here. Later empires would do the same thing. In medieval Europe, Jerusalem was the center. In China, the Middle Kingdom was the center. Every map is, in some way, a statement about importance. Now, in a practical sense, how useful were these maps for actual navigation? Probably not very, at least not by themselves. A Babylonian trader heading north would rely more on personal guides and memory than on a clay tablet. But the map served another purpose. It was a record of knowledge. It was proof that someone, somewhere, had tried to put the world in order. There's something deeply human in that. The Babylonians could have kept all this in their heads, but they didn't. They chose to press it into clay, to make it last. They were telling the future, this is what we know, this is how we see our world, and even if some of it turns out to be wrong, the act of recording it is an achievement in itself. When we look at that famous Babylonian world map today, with its tiny rivers and its mysterious outer lands, we're not just seeing geography, we're seeing the first steps toward abstract thinking about space. The idea that you can flatten the messy, three-dimensional, unpredictable world into a symbolic representation. It's the same leap your brain makes when you look at a subway map or a weather chart. So yes, by modern standards, the Babylonians' clay maps are crude, they're small, they're symbolic, they're sprinkled with myth, but they are also the ancestors of every map you've ever used. They carry the DNA of cartography, the belief that the world can be measured, drawn, and understood, and that belief, pressed into clay thousands of years ago, is still with us every time we open a map app and watch the little blue dot move. The clay world of Babylon may have been small, but it was the start of something big. If the Babylonians gave us clay maps the size of a coaster, the ancient Greeks looked at that and said, "Nice start. Now let's measure the whole planet." And they meant it. They were not shy about big ideas. Where earlier cultures mapped their own valleys and rivers, the Greeks asked questions like, how big is the earth? What shape is it? And can we figure that out with math and a few sticks? Spoiler, yeah. Let's start with a man named Eratosthenes. He was the head librarian of the Great Library of Alexandria, which basically meant he was the CEO of ancient knowledge. Imagine having the keys to the biggest book collection in the world, and instead of just reading quietly, you decide to measure the earth. That's the kind of overachiever we're dealing with. Eratosthenes had heard about a well in the city of Cyane, far to the south of Alexandria. On the summer solstice, at noon, the sun shone straight down into the well, lighting the water at the bottom without casting a shadow. That's a neat party trick, but to Eratosthenes, it was a clue. If the sun was directly overhead in Cyane, but cast a shadow in Alexandria at the exact same time, that meant the Earth's surface was curved. So he set up an experiment. In Alexandria on the solstice, he measured the shadow of a stick, technically a gnomon if you want to impress people at dinner parties. The angle of the shadow was about 7.2 degrees. Now here's where the math comes in. 7.2 degrees is 1/50th of a full circle. If he knew the distance between Alexandria and Cyane, he could multiply by 50 and get the circumference of the Earth. And how did he know the distance? He didn't have a car odometer or a drone. He hired people to walk it. Well, okay, he probably asked caravan leaders who had paced it out over years of travel. They estimated it at about 5,000 stadia. A stadion was a Greek unit of length. Not exactly consistent, but let's go with roughly 157 meters. Multiply 5,000 by 50 and you get about 39,350 kilometers. The modern value is just over 40,000. Eratosthenes was within a few hundred kilometers of the true figure, using nothing but shadows, pacing and geometry. Not bad for 200. This was a breakthrough. It showed that math could measure not just a field or a river, but the entire planet. And once you know the size of the Earth, your maps stop being guesswork and start being scaled models. You can say, if this is here and that is there, then this must be over there, and it actually works. But the Greeks didn't stop at measuring. They loved theorizing. Pythagoras, famous for his right triangle theorem, also believed the Earth was a sphere, partly because a sphere is the most perfect shape, and the Greeks loved perfection, but also because they noticed ships disappearing hull first over the horizon. They saw different stars when they travelled north or south. These clues added up. We're living on a ball. Then there was Hipparchus, a genius who took Babylonian star maps and turned them into a coordinate system. He invented latitude and longitude. Not quite the system we use today, but close. Latitude was easy enough. Measure the angle of the sun or a star above the horizon. Longitude was trickier because it required knowing the time in two different places at once. Without accurate clocks, that problem would haunt mapmakers for centuries. And let's not forget Ptolemy, the grand synthesizer. Around 150 CE, he wrote the Geographia, a massive collection of maps and instructions on how to make them. He refined the coordinate system, compiled data from travelers, and set down projection methods, ways of representing the spherical Earth on a flat surface. Ptolemy's maps weren't perfect. Some places were wildly distorted, and he missed entire continents. But his methods were so influential that they shaped mapmaking for over 1,000 years. When European explorers set sail in the 1400s, they still used Ptolemaic maps. One thing the Greeks were especially good at was mixing observation with deduction. If they couldn't measure something directly, they'd figure out a clever way around it. Want to know how far away the moon is? Watch a lunar eclipse and use geometry. Want to know the size of the sun? Same thing. They treated the world like a giant puzzle, and geometry was their favorite tool. Of course, their maps reflected their worldview, just like everyone else's. They placed Greece in a prominent position. The Mediterranean was the center, surrounded by Europe, Asia, and Libya, their name for Africa. Beyond that, unknown lands, often left blank or filled with speculation. Still, their willingness to measure and systematize set them apart. Let's pause to appreciate what this meant for travel. If you're a Greek sailor with access to even a crude coordinate system, you can describe a location without having to say sail toward the big rock that looks like a goat. You can say it's at this latitude and this longitude, and another sailor can in theory find it without ever having been there. This was revolutionary, and it all circles back to math. Triangles, circles, and ratios turned geography from storytelling into science. The Babylonians and Egyptians had done incredible work with local measurements, but the Greeks aimed for the globe. They wanted a universal system, something that could describe the whole Earth with numbers. That ambition is what makes this chapter in mapping so exciting. There's also a human side to all this. Imagine Eratosthenes explaining his earth-measuring experiment to his friends. They nod politely, then ask, "So will this help us find better wine?" Maybe not directly, but it's that combination of curiosity and practicality that drives human progress. You solve a problem because you can, and later you find out it's useful in ways you didn't expect. In a sense, the Greeks gave map-making its mathematical skeleton. Without it, later cultures would have been drawing pretty pictures with no framework. With it, they could hang details on a structure that made sense, that matched the real world. So next time you open a map app and see a little pin drop on a specific spot on the globe, remember, that precision started with people like Eratosthenes, Pythagoras, Hipparchus, and Ptolemy, people who stood in the sun with sticks, stared at stars and scribbled numbers on papyrus, and in doing so pulled the shape of the Earth out of the realm of myth and into the realm of math. And they did it without satellites, without computers, and without leaving their feet on solid ground. If ancient Greece gave map-making its mathematical bones, then Claudius Ptolemy came along and gave it muscles, skin, and a slightly bossy attitude. Ptolemy lived in the 2nd century CE in the Egyptian city of Alexandria, which at the time was basically the Wi-Fi hotspot of the ancient world. It was where knowledge came to hang out. Ptolemy wasn't just a geographer. He was also an astronomer, mathematician, and all around I'll just write the definitive book on everything kind of guy. His Geographia wasn't just one book. It was an 8-volume how-to manual for mapping the known world. And when I say how-to, I don't mean a vague list of tips like try drawing north at the top. No. This was a full instruction kit with coordinates for more than 8,000 locations. That's right, 8,000. Cities, mountains, rivers, islands, all pinned down with latitude and longitude. It's like the world's first giant spreadsheet of geography. If you wanted to make your own map, Ptolemy basically handed you the data and said, "Here you go, don't mess it up." The genius of Geographia was that it didn't just list places, it gave you the math to plot them on a flat surface. Ptolemy wrestled with the same problem every mapmaker faces. The Earth is round, but paper is flat. If you just peel the Earth like an orange and flatten it, everything gets distorted. So he proposed several projection methods, ways to transform the globe's coordinates into something that could be drawn without making Africa look the size of a postage stamp. He knew projection would never be perfect. Flattening a sphere is like trying to wrap a football with a sheet of paper. You have to crease it somewhere, but his math let mapmakers choose how to distribute those creases. Want the continents to keep their shapes, you'll have to accept that distances get a little wonky. Want distances to be accurate, shapes will stretch like pizza dough. These trade-offs are still part of mapmaking today. Ptolemy also believed the Earth was much smaller than it really is. He underestimated its circumference, which would later have interesting consequences. Fast forward to the 15th century, and Christopher Columbus is reading Ptolemy's figures, thinking, hey, Asia is just a short sail west from Europe. Spoiler, it wasn't. Ptolemy's math accidentally made Columbus think the globe was a lot more compact than reality. Without that mistake, Columbus might not have even tried. So yes, Ptolemy's atlas helped start the age of exploration, partly by being wrong. His worldview was also missing a few large items. No Americas, no Australia, Antarctica, not even a rumour. For Ptolemy, the known world was Europe, North Africa, and Asia, as far east as China. Everything else was a mystery. And in his maps, mystery often meant, here be oceans, or here be a giant southern continent we just made up to balance the map. He liked symmetry. And yet, Geographia was revolutionary. Before Ptolemy, maps were often hand-drawn without consistent scale or orientation. After Ptolemy, anyone who could read his instructions could make a map that matched someone else's map. That's a huge leap. It means two people on opposite sides of the Mediterranean could draw the same coastline with the same proportions without ever seeing it together. Imagine living in a time when most people's mental map of the world ended a few villages away, and then seeing a carefully plotted drawing of the entire known world. That's a shift in perspective. It's like someone handing you Google Earth after a lifetime of walking the same dirt road. Ptolemy didn't invent latitude and longitude, but he perfected their use. Latitude was measured from the equator, easy enough if you could measure the height of the sun or certain stars. Longitude was trickier. It was measured east or west from a prime meridian that Ptolemy placed through the Canary Islands. Why there? Probably because it was as far west as anyone in his circle had sailed. One thing that made Ptolemy's atlas so enduring was its instructions for reproduction. You could copy the coordinates from his tables and, using his projection formulas, redraw the entire map accurately. This meant Geographia was more than a book. It was an algorithm for turning numbers into geography. The printed map wasn't the point. The method was. Of course, over time, copying errors crept in. Monks and scholars copying manuscripts might misread a number, or accidentally swap a coordinate's digits. Multiply that by centuries, and some maps based on Ptolemy's data ended up with towns floating in the sea or mountains in the wrong hemisphere. But the framework held. The idea that you could locate a place anywhere on Earth with just two numbers stuck around and still runs your GPS today. Ptolemy himself probably never travelled far from Egypt. Most of his information came from earlier sources, Greek, Roman and Persian travellers, plus a healthy dose of sailor gossip. Some of it was surprisingly accurate. Some of it was, trust me, my cousin saw it. But Ptolemy's genius was organising it all into a coherent system, even if the data wasn't perfect. Let's be honest. Some of his coastline shapes look like they were drawn by someone who had never actually seen a coastline. The Mediterranean is squished, India is tilted, but the fact that you can even recognize them as the Mediterranean and India is a huge deal for the 2nd century. Here's the other thing. Ptolemy's Geographia disappeared from European libraries for over 1,000 years. It survived in the Islamic world, translated into Arabic, where scholars preserved and expanded on it. When it finally made its way back to Europe in the Renaissance, it was like an old master returning with blueprints for a much bigger world. Mapmakers devoured it, adapted it, and used it to chart new discoveries. So Ptolemy's atlas wasn't just a product of its time. It became a time traveler. It shaped maps in the Roman era, vanished, then reshaped them in the 15th century. That's staying power. If you strip away the ancient names and the missing continents, the core of Ptolemy's work still beats inside every map you've ever used. The idea that the Earth can be divided into a grid, and that every place has a unique address on that grid, whether you're plotting a trade route in 50 CE or looking for the nearest pizza place in 2025, you're living in Ptolemy's world. And that's the magic of it. He took the messy, scattered scraps of geographical knowledge and gave them a structure so solid that, even 2 millennia later, we still think about space the way he taught us to. Ptolemy may have been off about the size of the planet, but he was dead right about how to map it. When the Roman Empire crumbled in the West, a lot of knowledge scattered with it. Trade routes shrank, cities shriveled, and the grand libraries that once collected the world's wisdom either burned, rotted, or got turned into convenient goat barns. But there were survivors in this intellectual storm, and many of them wore robes, lived in stone buildings, and were really into both God and ink. These were the medieval monks. To them, mapmaking wasn't about exact measurements or precise coastlines. It was about showing the world as a story. And the story was, above all, a Christian one. If you asked a monk in, say, the year 1250 to draw the world, you were not going to get a Ptolemaic grid. You were going to get a mappa mundi, a map of the world that looked like a cross between a theology textbook and a medieval Pinterest board. The most famous of these is the Hereford Mappa Mundi. In England, a massive skin of calf parchment almost as tall as a person. It shows the known world, Europe, Asia and Africa, but not in any proportion you'd recognize. Jerusalem is in the center, because in this worldview the spiritual heart of the earth had to be the geographical one too. East is usually at the top, not north. This made sense if you thought of the Garden of Eden as being in the east. After all, Genesis says it's in the east. And what better place to put paradise than the top of the map? So if you're used to modern maps with north up, these medieval ones feel like they're flipped sideways. What's fascinating is how much these maps are less about navigation and more about meaning. Rivers, mountains and cities are there, sure, but so are biblical scenes, monsters from travelers' tales and moral lessons. In the Hereford map you'll find illustrations of the Tower of Babel, the Garden of Eden and various creatures like unicorns and men with faces in their chests. These weren't mistakes in the medieval mind. They were part of the world as people then understood it. A mix of scripture, classical texts, and a sprinkling of rumour from the few who travelled far. The maps were drawn in monasteries by monks who were also copyists. A single map could take months or years, with every river and city carefully inked and painted with bright colours. If you've ever tried calligraphy, You know how much patience this takes. Now imagine doing that with a quill pen, no electric light, and a cat trying to sit on your parchment. These maps were not meant to be stuffed in a saddlebag and carried into the wilderness. They were showpieces, hung in churches or kept in libraries as teaching tools. They were there to explain the world's order, a divine order to people who might never travel more than 20 miles from home. That's not to say medieval people didn't care about geography. Pilgrimages were huge in this era. People traveled to Santiago de Compostela, Canterbury, Rome, Jerusalem, and while they didn't have portable road maps like we do, they had guidebooks called itineraria, lists of routes, towns, and distances between them. You could think of them as text-only maps. A monk could use a mappa mundi to teach a pilgrim about the holy sites, then hand them a written itinerary for the actual journey. There was also another style of medieval map, the Portolan chart. These started appearing around the 13th century and were used by sailors in the Mediterranean. They were much more accurate for coastlines and harbours. No unicorns in sight, and they came from a more practical tradition of seamanship. But that's another story. The monastic mappa mundi was its own thing entirely. What's charming about these monastic maps is the way they compress everything into one surface. The known continents are squashed together so that the map can include both the real and the symbolic. There's a kind of everything important in one picture vibe. Think of it like a medieval infographic, not there to help you drive from Paris to Rome, but to help you understand the world in a single glance. The proportions are creative. Africa might be a sliver, while Asia takes up half the map. Rivers bend at odd angles to fit in famous cities. Mountains might be drawn as rows of pointy cones, not because anyone thought mountains actually look like that, but because that's the easiest way to say mountains in a tiny drawing. From a mathematical perspective, these maps are the opposite of Greek geometry. There's no consistent scale, no projection, no attempt to keep distances proportional. But they do tell us something important about the mindset of the time. Maps are not just about physical space. They're about how we think the world should be arranged. In this case, arranged around God, Scripture, and the salvation of the soul. Of course, that didn't stop the occasional embellishment. Heard about a strange island? Pop it on the edge of the map. Someone swears they met a tribe of people with dog heads. Into the margins they go. These flourishes kept the maps interesting, and maybe helped bring in a few extra pilgrims curious to see what the land of Gog and Magog looked like. One could argue that in their own way these monks were preserving a kind of data visualization, not the data of precise geography, but the data of cultural memory and moral teaching. They were saying, this is the world as we understand it. Spiritually and historically, it was a map of the mind, as much as of the land, and there's something oddly comforting about that. We live in a time where maps are ruthlessly accurate, down to the exact shape of your neighbour's garden shed. But the monks' maps remind us that for most of history, maps were also art, narrative, and a little bit of wishful thinking. They weren't just tools to get you from point A to point B, they were ways of making sense of existence. So if you ever stand before one of these giant medieval maps, don't judge it by its geography. Judge it as a piece of storytelling. Every crooked river and misplaced city is part of a larger message, and somewhere in the candlelit silence of a monastery centuries ago, a monk dipped his pen, added a tiny drawing of Jerusalem, and thought, yes, this is the world. While monks in Europe were drawing maps full of unicorns and rivers that bent to fit Bible stories, another part of the world was quietly, or not so quietly, launching a cartographic revolution. From the 8th to the 14th century, the Islamic world was in its golden age, and it was busy measuring, mapping, and calculating like there was no tomorrow. Baghdad, Cairo, Damascus, Cordoba. These cities weren't just political centers, they were knowledge hubs. Scholars there inherited the works of the Greeks, preserved them, translated them into Arabic, and then did what all great scientists do. They improved them. They didn't just read Ptolemy. They checked his math, corrected his mistakes, and expanded his maps with new information from Africa, Asia, and beyond. One of the stars of this era was Muhammad al-Idrisi. He was born in Ceuta, modern-day Spain-Morocco border, travelled widely, and ended up in Sicily at the court of King Roger II. Yes, a Muslim scholar working for a Christian king. It turns out science is often more interested in truth than in borders. Roger wanted a map of the entire known world, and al-Idrisi delivered his masterpiece, the Tabula Rogeriana. Completed in 1154, was not just a map, but an entire geography book. It took 15 years to make, and included descriptions of more than 70 regions covering Europe, Asia, and Africa. Al-Idrisi gathered data from travelers, merchants, and explorers, cross-checking it to weed out the obvious nonsense. He even employed surveyors to take fresh measurements. The Tabula Rogeriana is beautiful, but to modernize, it's upside down. South is at the top, north at the bottom. This wasn't a mistake, it was a choice. Many Islamic maps at the time were oriented with south up, partly due to cultural and navigational traditions. If you're used to north being up, it's a bit of a brain twist, but it works just as well. What makes al-Idrisi's work remarkable is its accuracy for the time. Coastlines are recognizably shaped, distances are often reasonable, and the placement of cities is far better than in most European maps of the same era. His map shows the full length of the Nile, the outline of the Arabian Peninsula, and trade routes reaching into the Indian Ocean. The Islamic Golden Age also gave us one of the greatest feats of geographic measurement, the calculation of the Earth's circumference by al-Mamun's scholars in the 9th century. Al-Mamun was a caliph in Baghdad, who basically said, Eratosthenes did pretty well, but we can do better. He sent 2 teams of surveyors out into the desert, one heading north, the other south. They measured the distance needed for a star's position to change by 1 degree in the sky. Multiply that distance by 360, and you get the circumference of the Earth. The result? About 40,248 kilometers. That's within a few dozen kilometers of the modern value. Not bad for people with no cars, no satellites, and no laser rangefinders. Just careful observation, math, and probably very sore feet. Astronomy and cartography were tightly linked in the Islamic world. Accurate maps of the stars were essential for navigation and for determining the direction of Mecca for prayer. This led to incredible advancements in instruments like the astrolabe, a kind of analog calculator made of brass that could tell you your latitude, the time of day, and even when the sun would rise. If Google Maps had a 9th century ancestor, it was the astrolabe. Islamic cartographers also excelled at city maps. In Baghdad, there were detailed plans showing markets, mosques, gardens, and canals. In Damascus and Cairo, maps helped manage complex water systems. This wasn't just about exploration. It was about managing life in bustling urban centers. And here's the fun part. Islamic scholars didn't just keep this knowledge to themselves. Through trade, diplomacy, and sometimes conquest, their maps and methods flowed into Europe. By the 12th century, translations of Arabic geographical works were circulating in Spain and Italy, influencing European mapmakers. When the Renaissance hit, a lot of the new knowledge in Europe was really well preserved and upgraded knowledge from the Islamic Golden Age. Al-Idrisi's Tabula Rogeriana remained one of the most accurate world maps for centuries. Even explorers in the 15th and 16th centuries would have recognized its outlines. His descriptions of Africa, in particular, filled in gaps that European maps often left blank. One thing that stands out about Islamic cartography is the balance between science and art. These maps are not just functional, they are gorgeous. Delicate calligraphy labels each city and region. Geometric patterns frame the maps, blending mathematical precision with aesthetic beauty. It's a reminder that in this culture, knowledge and beauty went hand in hand. From a mathematical point of view, the Islamic Golden Age was a bridge, taking Greek geometry, refining it, and then handing it off to the Renaissance. They kept the coordinate systems, improved measurement techniques, and even experimented with different projections. Without this bridge, the jump from Ptolemy to Columbus would have been a lot messier and probably a lot slower. So the next time you look at a clean, detailed modern map, remember that part of its DNA runs through the deserts of the Middle East, the libraries of Baghdad, the courts of Sicily, and the workshops of craftsmen engraving brass astrolabes. And remember Al-Idrisi, who with a pen, parchment, and years of listening to traveller stories, drew a world that was as accurate as humanly possible in the 12th century, south up, north down, and everything in between meticulously recorded. In a way, the Islamic Golden Age cartographers were doing exactly what great map makers have always done, combining curiosity, math, and the best information available to create a picture of the world that could inspire the next journey. Picture this. You're standing on the deck of a creaky wooden ship in the year 1450. The wind smells like salt, the deck smells like fish, and the guy in charge of steering has exactly 2 navigational tools, his eyes and a pretty good memory. There's no GPS, no radar, and not even a halfway decent map once you leave the coast, you know. The moment land disappears over the horizon, you are, in the most technical of maritime terms, guessing. And people did a lot of guessing. This was the great age of dead reckoning, a navigational method that sounds a lot more confident than it really is. The idea was simple. You sail in a certain direction for a certain amount of time at a certain speed, and from that you figure out where you are. The problem is that certain was rarely certain. Speeds were estimated by throwing a piece of wood overboard and timing how long it took to drift past the stern, with a sandglass that may or may not have been accurate. Direction was guessed with a compass, which was better than nothing but still useless if you didn't know exactly where you started. The big problem at sea was longitude. Latitude was manageable. You could figure that out by measuring how high the sun got at noon, or how far certain stars were above the horizon. That's why sailors like to hug lines of latitude. If you could sail west along the same latitude, you'd eventually get where you were going. Probably. But longitude, that's a whole different beast. Longitude requires knowing the time difference between where you are and some reference point, like your home port. And without an accurate clock, which wouldn't exist until the 18th century, you were out of luck. At sea, pendulum clocks were useless, because the ship never stopped moving. So for most of history, longitude was a mystery. Ships wandered, some missed their destinations by hundreds of miles, some missed entire continents. Sailors did have other tricks. One was reading the water, noticing changes in its colour, temperature, or the type of seaweed floating around. Another was following birds, assuming they were headed back to land. There were also ocean swells, which have different patterns depending on the shape of the nearest coastline. The Polynesians mastered this art, long before Europeans ventured far from shore, using nothing but wave patterns, stars and mental maps to cross thousands of kilometers of open ocean. But for most sailors in Europe's age of exploration, the ocean was a blank canvas. Sometimes literally, medieval and early Renaissance maps often just stopped where the land ended. Beyond that was the mare incognitum, the unknown sea. Sometimes there were little drawings of sea monsters, partly as decoration, partly as a warning. After all, if you don't know what's out there, you might as well imagine a giant squid with a taste for ships. The leap into the unknown took guts. Leaving sight of land was terrifying. For coastal sailors, the horizon was the edge of their world. Once you crossed it, you couldn't see familiar landmarks. The ocean became a featureless, moving plain. It's easy for us to say, oh, just keep going west. But imagine sailing into a fog where the water and sky merge into one endless grey, with no clue whether you're headed toward paradise or a watery grave. And yet, people did it. Driven by trade, exploration, curiosity, and sometimes desperation, ships pushed farther and farther. They learned quickly that the ocean was not random. It had patterns. The trade winds, for example, blow steadily from east to west in the tropics, making it easier to sail toward the Americas than back from them. The Gulf Stream carries warm water north from the Caribbean, speeding ships toward Europe. These were the highways and back roads of the ocean, and sailors who knew them could shave weeks off a voyage. Mathematics slowly started creeping into this process. Charts began including compass roses, showing directions for navigation. Sailors used cross staffs and later astrolabes to measure the angle of the sun or a star, giving them their latitude. The more accurate their measurements, the less likely they were to end up hopelessly lost. But until longitude could be solved, open ocean navigation remained part science, part art, and part sheer luck. Let's be clear, a lot of early exploration voyages failed. Ships sank, crews starved, some expeditions were never heard from again. And yet, the rewards were so great, new trade routes, exotic goods, spices, gold, that people kept trying. Each voyage brought back not just cargo, but also information. A coastline sketched here, a new island marked there, a dangerous reef noted for the next crew. Slowly, the blank spaces on the maps began to shrink. By the late 15th century, navigation had improved enough for daring trips like Columbus's westward voyage, or Vasco da Gama's trip around Africa to India. But even these legendary journeys were full of navigational improvisation. Columbus didn't know exactly where he was most of the time. Vasco da Gama had to rely heavily on local pilots in the Indian Ocean who actually knew the waters. The truth is, the real masters of the unknown were often the local sailors whose skills never made it into European history books. And there's the irony. Sailing into the unknown wasn't always unknown to everyone. The Polynesians had been doing it for centuries. Arab navigators crisscrossed the Indian Ocean with confidence. West African sailors travelled along their coastlines and beyond. What was unknown depended on whose map you were looking at. Still, for the Europeans who were expanding their reach in the 1400s and 1500s, each new voyage was like peeling back a piece of the world's curtain. The math and the maps got better. Cartographers back home stitched together the reports from dozens of voyages, refining coastlines, adding islands, and slowly erasing the monsters. Of course, some monsters stuck around, partly because they were good decoration, partly because the ocean is home to strange creatures. Sailors told tales of whales the size of mountains, of storms that seemed alive, of waters that boiled, which might have just been volcanic activity, but still creepy. These stories made their way onto maps in the form of little illustrated warnings. In the end, sailing into the unknown was as much about courage and stubbornness as it was about navigation. The tools were crude, the risks were enormous, but the pull of the horizon was stronger, and every time a ship returned, it brought back more than spices or silver. It brought back new knowledge that would help redraw the world. So next time you look at a perfectly accurate digital map on your phone, remember the sailors who ventured out with nothing but the wind, the stars, and a rough idea of which way west was. They didn't just explore the world, they made it possible for the rest of us to know it. If you wanted to make a sailor in the 1600s nervous, you didn't have to mention pirates, storms, or scurvy. You just had to say one word: longitude. Latitude was the easy sibling. You could figure out your north-south position just by looking at the sun at noon or checking the height of the North Star. You didn't even need to be good at math. A cross staff or an astrolabe would give you a number you could look up in a handy table. But longitude? That was the riddle no one could crack. Longitude is your east-west position on Earth. To know it, you have to know the time difference between where you are and some fixed location, like Greenwich in England. Every hour of time difference equals 15 degrees of longitude. Sounds straightforward, except for one big problem. You need a clock that works perfectly at sea. And the sea, it turns out, is where clocks go to die. Pendulum clocks lose their rhythm when the ship pitches and rolls. Temperature changes make parts expand and contract, throwing off the timing. Salt air rusts gears. Sand glasses are fine for timing short tasks, like how long it takes to boil your cabbage, but they're useless for keeping the exact time over weeks. Without a good clock, longitude was guesswork. Sailors relied on dead reckoning, estimating how far they'd travelled east or west since their last known point. But ocean currents, storms, and steering errors all threw that off. By the end of a long voyage, your calculated position might be off by hundreds of miles. And that's where the broke kings part comes in. Getting longitude wrong could be catastrophically expensive. In 1707, a British fleet miscalculated its longitude and smashed into the Scilly Isles in a storm. 4 warships went down. Nearly 2,000 sailors died. The disaster was so shocking that it spurred Parliament to pass the Longitude Act of 7. The Longitude Act was basically a giant cash prize challenge. The British government offered £20,000, millions in today's money, to anyone who could find a practical way to determine longitude at sea within half a degree. The race was on. Astronomers, mathematicians, clockmakers, and a few outright charlatans all threw in their ideas. Some proposals were ingenious. Others were absurd. One man suggested dropping anchored ships along major sea routes, each with a clock set to Greenwich time, so passing ships could check their watches. The logistics of keeping hundreds of ships anchored in the middle of the ocean were apparently not a concern for him. Astronomers pushed the lunar distance method, using a sextant to measure the angle between the moon and certain stars, then comparing that to tables predicting the moon's position. If you could do the math, and it was a lot of math, you could figure out the time in Greenwich, and thus your longitude. The problem? This required crystal clear skies, a steady hand, and the patience of a saint. It was accurate, but exhausting. Then there was John Harrison, a self-taught English clockmaker who became the unlikely hero of the longitude saga. Harrison spent decades designing and building sea clocks that could keep perfect time despite the motion of a ship. His first attempts were massive machines that looked more like furniture than instruments. Over the years he refined them into smaller, more reliable designs, culminating in the H4, a watch-sized timekeeper that was accurate to within seconds after an 81-day sea voyage. Harrison's work should have made him an instant winner of the Longitude Prize. But politics, skepticism, and stubborn bureaucrats got in the way. The board of Longitude was dominated by astronomers who favoured the lunar method, and they weren't eager to hand over the prize money to a clockmaker. Harrison spent much of his life arguing, demonstrating, and refining his designs before finally receiving most of the prize, and only after King George III personally intervened. Harrison's marine chronometers changed everything. With an accurate clock set to the time at a fixed location like Greenwich, a ship could determine its longitude simply by comparing local noon, when the sun was highest, to the clock's time. The difference told you how far east or west you were. No more guessing, no more praying to hit land where you expected. The ripple effects were enormous. Trade became safer and faster. Naval power became more reliable. Exploration could be done with far less risk of ending up hopelessly off course. Maps became more accurate as ships brought back precise coordinates from their voyages. It's hard to overstate how big this was. For centuries, longitude was the missing puzzle piece in global navigation. Solving it didn't just make sailing easier, it reshaped geopolitics, trade, and science. Nations could project power more effectively, merchants could deliver goods faster, and cartographers could redraw the world with a level of precision that would have seemed like magic 100 years earlier. And all because of a clock. Well, a clock and a lot of stubbornness. Harrison spent over 30 years perfecting his designs. The lunar distance method kept improving too, and in the end, both were used side by side for decades. But Harrison's chronometer was the real game changer. Today, longitude barely crosses our minds. GPS tells us exactly where we are, down to a few meters, anywhere on Earth. But that luxury sits on top of centuries of trial, error, arguments, and the occasional disaster. The problem that broke kings wasn't just about measuring east and west. It was about proving that human ingenuity could solve a problem that the ocean had been throwing at us since the first time someone lost sight of shore. It was about persistence, and maybe a little about the satisfaction of showing a room full of skeptical astronomers that a good clockmaker could beat them at their own game. If you think the drama of maps is just about paper and ink, think again. In the age of exploration, a good map was worth more than gold, and in some cases, it was gold. Maps could decide the fate of empires, dictate who controlled the spice trade, and settle or start wars, which meant that in the 15th, 16th, and 17th centuries, maps weren't just tools, they were weapons. The two biggest players in this game early on were Spain and Portugal. In 1494, they signed the Treaty of Tordesillas, a document that basically said, let's divide the world in half, you take this bit, we'll take that bit. They drew an imaginary line down the middle of the Atlantic Ocean, about 1,170 kilometers west of the Cape Verde Islands. Everything west of the line was Spain's to explore and claim. Everything east was Portugal's. It sounds neat and tidy until you realize they didn't actually know where half the world was yet. This line meant that accurate maps were suddenly not just handy, they were legally binding. If a new island was found, its position relative to that invisible line could determine which crown it belonged to. That's why maps became top-secret state property. In Portugal, it was literally a crime punishable by death to share detailed navigational charts with foreigners. Their Padrão Real, the official master map, was locked away in the royal archives like a crown jewel. Espionage became part of the cartographer's job description. Explorers might return from a voyage with more than just stories of new lands. They brought sketches, measurements, and coastline notes, all of which could be stolen, copied, or accidentally misplaced. Rival nations would send spies to ports to eavesdrop on sailors, bribe ship captains, or even sneak into mapmakers' workshops at night. The Dutch were particularly good at this. In the late 1500s and early 1600s, as they built their trading empire, they relied on stolen Portuguese charts to reach lucrative destinations in the East Indies. One famous case involved the capture of a Portuguese ship, the Santa Catarina. Among its cargo was a set of detailed maps and navigational instructions for sailing to the Spice Islands. The Dutch East India Company published these as a book, breaking Portugal's monopoly and opening up the trade routes to others. Sometimes the rivalries were more about one-upmanship than outright theft. In the 16th century, the Spanish cartographer Diego Ribeiro created the Padrón Real for Spain, a master map that was continually updated with the latest discoveries. Not to be outdone, the Portuguese maintained their own secret master chart, updated in parallel. Both nations claimed theirs was more accurate. But since no one outside the inner circles could see both at once, the argument was mostly just national pride with a side of paranoia. The British eventually got into the game too. By the 18th century, they were producing detailed naval charts that gave them a huge advantage in projecting power across the globe. But even then, secrecy was the rule. The Admiralty's Hydrographic Office guarded its surveys fiercely, and ship's logs containing mapping information were classified. If a captain lost his charts to an enemy, it was a scandal. It wasn't just national rivals. Sometimes individual mapmakers clashed. In the early 1500s, the German cartographer Martin Waldseemüller made history by being the first to label the newly discovered lands in the West as America, after the explorer Amerigo Vespucci. This annoyed plenty of people who thought Columbus deserved the credit. Waldseemüller himself later seemed to have second thoughts. Later editions of his maps quietly dropped the name. But by then, it was too late. The label had stuck. Other rivalries were over accuracy. Gerardus Mercator, the Flemish cartographer who gave us the famous Mercator projection, faced criticism from those who preferred other ways of flattening the globe. His projection made navigation easier for sailors. Straight lines on his maps represented constant compass bearings. But it also distorted land sizes, making Europe and North America look bigger and Africa look smaller. His critics argued this gave a skewed view of the world, but sailors loved it, because it worked for plotting courses. Accuracy, it turned out, depended on what you needed the map for. And sometimes, maps were deliberately wrong. A little trick known as a trap street, or cartographic fake. By adding a tiny fictional island, a non-existent bend in a river, or a made-up place name, a cartographer could catch anyone who copied their work without permission. If your rival's map had the same fake feature, you had proof they'd stolen it. The idea is still used today in digital maps, though now the fakes are often tiny changes to street layouts instead of imaginary islands. These rivalries pushed cartography forward. Every nation wanted to outdo the others with more precise surveys, better charts, and faster updates. Expeditions weren't just about planting flags. They were about collecting data that could be turned into navigational gold. The faster your maps improved, the faster you could dominate trade, colonization, and warfare. But there was a cost. For centuries, ordinary people had no access to the best maps. If you were a merchant without the right connections, you had to make do with outdated or incomplete charts, which could mean longer voyages, lost cargo, or shipwreck. It wasn't until the 19th century, with the rise of printed atlases for the general public, that high-quality maps became widely available. Looking back, it's almost funny to think of cartographers as shadowy figures in an international spy game. We picture them hunched over desks with compasses and rulers, but in the age of exploration, they were also at the center of cloak-and-dagger politics. A single new coastline sketched in a captain's log could spark a rush to claim it, or a quiet mission to make sure no one else ever saw it. So the next time you glance at a world map and think it's just a piece of paper, remember, behind those clean lines and tidy labels are centuries of rivalry, theft, and intrigue. The history of maps isn't just about finding the world, it's about fighting over it. If you've ever looked at a map so accurate it makes you think, wow, somebody really measured everything, you can probably thank triangulation. This is the method that turned mapping from walk there and draw what you see into stay in one spot and measure with math. And it's brilliant in its simplicity. Here's the basic idea. Instead of trudging across every hill, swamp, and cranky farmer's field to measure distances directly, you measure one side of a triangle, a baseline, really carefully. Then you measure angles from each end of that baseline to a third point somewhere off in the distance. From that, geometry does the rest. You can figure out the other sides of the triangle without ever setting foot on them. Chain enough triangles together, and you can map an entire country without leaving your tee. The magic behind this is plain old trigonometry. Yes, that stuff you may have once met in school and tried to avoid making eye contact with. Triangulation uses sine, cosine, and tangent. But in the field it comes down to this. If we know this side, and we know these two angles, the rest of the triangle is ours. The first recorded champion of triangulation was a Dutchman named Willebrord Snell. In the early 1600s, he used it to measure the distance between 2 points in the Netherlands without walking the whole thing. This was big news. Imagine telling a 17th century surveyor, you can measure a river without swimming across it. That's coffee-spitting level excitement. Triangulation exploded in popularity in the 18th and 19th centuries. Why? Because it worked for big projects. The French used it to measure the meridian arc from Dunkirk to Barcelona, a massive effort that helped define the meter as a unit of measurement. The British used it for the Great Trigonometrical Survey of India, a decades-long project that mapped the subcontinent with extraordinary precision. The method required two main tools: something to measure the baseline, and something to measure angles. For the baseline, surveyors used chains, rods, or later steel tapes. These were laid out carefully, often over flat, open ground, with corrections for temperature, because metal expands in heat and contracts in cold. Yes, they were that picky. If the baseline was wrong, every other distance calculated from it would be wrong too. For angles, they used instruments like the theodolite, a kind of super-accurate telescope on a swivel, with angle markings. You'd set it up at one end of the baseline, aim it at a distant point, read the angle, then repeat from the other end, add some math, and you've got your triangle. The beauty of triangulation is how it scales. Once you have your first triangle, you can use its sides as baselines for more triangles, leapfrogging across the landscape. You don't need to measure every side of every triangle, just one in each group, plus the angles. That's a huge time saver. Of course, out in the field, this wasn't all neat diagrams and polite math. Surveyors had to set up instruments on windy hills, peer through heat haze, and haul heavy gear through forests. They also had to negotiate with landowners who were not thrilled about strangers camping in their fields to look at a hill with a funny telescope. In Britain's survey of India, the triangulation chains were so long, over 100 feet, and so heavy that it took a team of men to carry them. The surveyors dealt with wildlife, monsoons, and the occasional suspicion that they were spies, which in a way they were. Mapping is a kind of intelligence gathering. Triangulation also went vertical. It wasn't just about plotting coastlines or political borders, it was used to calculate the height of mountains. You'd measure angles to the peak from two known points, then let the math do the climbing. This is how the British calculated the height of Everest long before anyone set foot on the summit. They were off by less than a metre. Not bad for people who did their work sitting on folding chairs with tea mugs. The method's accuracy was so good that by the 19th century, governments were building entire networks of triangulation points. These were often marked by permanent structures, stone cairns, iron markers, even small towers, so that future surveyors could reuse the same reference points. Some of these markers still exist today, quietly sitting on hilltops, relics of a time when measuring the world was done with chains, angles, and stubbornness. One of my favourite parts of triangulation history is the mix of seriousness and absurdity. On the serious side, it underpinned everything from national borders to scientific research. On the absurd side, there are records of surveyors waiting weeks for the perfect clear day to take one angle measurement, only for a cow to wander in front of the target at the crucial moment. There's also the human element. Triangulation surveys often took years, even decades. The people who started them didn't always live to see them finished. Imagine spending your career measuring one triangle after another, knowing you're building something bigger than yourself. A map so accurate it could guide armies, merchants, scientists, and explorers for generations. In a way, triangulation was the land-based version of solving longitude at sea. It turned mapping into a precise science rather than an art based on close enough, and it had the same geopolitical impact. Better maps meant more efficient governance, stronger trade, and yes, more effective conquest. Empires loved triangulation because it gave them control in lines and numbers. Today we've replaced physical triangulation with satellites and GPS, but the principle is the same. Measure a baseline, or in GPS's case, use the speed of light. Measure angles or time differences, and let geometry tell you where you are. The math hasn't changed, we've just swapped steel chains for orbiting clocks. So next time you see a perfect straight border on a map or a topographic chart with spot-on elevation lines, remember the long chain of triangles behind it. Remember the surveyors squinting through theodolites on windy hills, the chains clinking as they were laid out on dusty plains, and the quiet satisfaction when a network of points finally closed with near-perfect precision. Triangulation was, and still is, the art of letting math walk the land for you. Sometimes science and politics mix in ways that are brilliant. Other times they mix in ways that make you shake your head and say, "You did what for how long?" The French Meridian project was a bit of both. The year was 1792. France had just chopped off its monarchy and was in the mood for radical ideas, not just in politics but in measurement. The revolutionaries wanted a new, rational system that would replace the chaotic mess of old units, feet that varied from town to town, ells, cubits, toises, leagues, each with different values depending on who you asked. They wanted a universal unit, based on something natural, unchanging, and immune to local bias. The result? The meter. 1/10,000th of the distance from the North Pole to the equator, along the meridian that passes through Paris. Simple in theory, brutal in practice. Because to define the meter, they first had to measure that meridian, precisely. Enter two men, Jean-Baptiste Delambre and Pierre Méchain. Their mission, measure the arc of the meridian between Dunkirk in the north and Barcelona in the south. This meant a triangulation survey spanning nearly 1,000 kilometers, across mountains, rivers, farmland, and, because this was revolutionary France, occasional mobs suspicious of men carrying strange instruments. Delambre, took the northern section, Meishan took the southern. Both were skilled astronomers and surveyors, and both were perfectionists, which was good for science but not great for their sanity. The job involved measuring a series of baselines with extreme accuracy, then using triangulation to connect them into a continuous chain of triangles stretching down the meridian. Every angle was measured multiple times with large, heavy repeating circles, instruments so delicate that moving them without damage was an ordeal. And this was the easy part. The hard part was convincing local villagers that you weren't a spy or a tax collector. Remember, this was the middle of a political revolution. Armed bands roamed the countryside. Rumors spread quickly. Why is that man staring through a telescope at our church tower? Could escalate into he's signaling the enemy. More than once, Delambre and Meishan were detained by authorities, questioned for hours, and occasionally threatened with violence. Meishan's section took him into the Pyrenees, where the terrain was spectacular but punishing. He had to haul equipment up steep, rocky slopes, build observation platforms, and deal with weather that could change from sunny to deadly in minutes. At one point, he became obsessed with a small discrepancy in his star measurements, a tiny error of just a few arc seconds. Rather than shrug it off, he spent months remeasuring, refusing to move on until he was satisfied. His perfectionism turned into an obsession that haunted him for the rest of his life. Delambre's section wasn't a picnic either. In the north, he had to measure across flat farmland, which meant building tall wooden towers to get line of sight between triangulation points. Setting these up in the middle of someone's wheat field often led to arguments. In one village, locals assumed the strange apparatus was some kind of machine for stealing sunlight. Despite the challenges, both men pressed on. By 1798, after years of work, they had their results. Combined, the two halves of the survey gave the length of the Paris meridian arc between Dunkirk and Barcelona. From that, they extrapolated the total length of the quarter meridian from pole to equator, and from that, they defined the meter. It was an extraordinary achievement, but not a perfect one. Meishan's obsession with tiny errors meant he knew there were slight inaccuracies in his southern section. He didn't tell anyone at the time, but the guilt stayed with him. It wasn't until decades later that researchers found his original notes and realized the flaw was so small it barely mattered. The new metric system, meter, kilogram, litre, was officially adopted in France in 1799. It would spread slowly, but the meridian survey was the foundation. For the first time, a unit of length wasn't based on a king's body part or an arbitrary stick, but on the size of the earth itself. The human cost, though, was high. Meishan never truly recovered from the strain of the project. He died in 1804, still fretting over his measurements. Delambre lived longer, becoming a respected figure in French science, but he never forgot the sheer grind of those years in the field. What's striking is how much of this meridian madness was driven by ideals. The revolution wanted equality, and that meant equality in measurement too. If a meter in Paris was the same as a meter in Marseille or Madrid, no one could manipulate units for local advantage. The meter was meant to be universal, rational, and free from politics, though ironically, it was born out of a very political time. From a mathematical standpoint, the meridian survey was a triumph of triangulation on a grand scale. The network of triangles was so precise that errors of a few centimeters over kilometers of distance were considered unacceptable. The survey's accuracy was limited only by the tools of the time, and even those were pushed to their limits. Today, the meter is defined differently, by the speed of light, but the spirit of that revolutionary project lives on. Every time you use metric units, you're connected to Delambre and Meishan trudging across France and Spain with their towers, chains, and star charts, determined to measure a slice of the planet with Orthus' absurd precision. It's a reminder that behind every simple unit we take for granted is a story, and sometimes that story involves years of mud, mountains, political danger, and an argument with a farmer about why you're on his roof with a telescope. If France's Meridian project was a bold sprint to define the meter, Britain's Great Trigonometrical Survey of India was a marathon, a marathon that lasted more than 70 years. This was mapping on an imperial scale, the cartographic equivalent of painting the Sistine Chapel ceiling while someone keeps extending it another few meters every year. It started in 1802 with one big idea: map the entire Indian subcontinent with the precision of a finely tuned watch. Britain's East India Company wanted accurate maps for administration, taxation, and, let's be honest, controlling its vast colonial holdings. But this wasn't just a political project. For the surveyors, it was also a scientific mission. They wanted to measure the size and shape of the Earth as precisely as possible in the southern hemisphere. The man who got it rolling was William Lambton, a meticulous surveyor with a love for precision that bordered on obsession. Lambton began by measuring a baseline near Madras, now Chennai, with steel chains, each link carefully calibrated. The baseline was over 12 kilometers long, and every measurement had to be corrected for temperature, tension, and even the curvature of the Earth. If you think that sounds excessive, remember, any error here would ripple through the entire network of triangles, throwing off the whole map. The terrain was unforgiving. India is not flat, at least not in the way you'd hope when you're dragging survey equipment across it. There were dense jungles, scorching plains, and mountain ranges that laughed at the idea of easy access. Setting up a theodolite on a windy hill was tricky enough. Doing it in the middle of a tiger's hunting ground was something else entirely. Speaking of theodolites, the survey used one that was a beast. Built by Jesse Ramsden. It weighed over half a ton and had to be carried on the backs of multiple elephants. Just moving it from one triangulation point to another was an operation in itself. Once set up, it allowed for angle measurements so precise that surveyors could detect errors of just a few seconds of arc, the kind of accuracy that makes math teachers weep with joy. After Lambton's death in 1823, the project passed to George Everest. Yes, that Everest, the mountain was later named after him. Everest shared Lambton's passion for accuracy and his intolerance for sloppy work. He also had to contend with all the fun hazards of surveying in the tropics: malaria, dysentery, monsoons, and the occasional suspicion from locals who thought the strange instruments might be tools for sorcery. The survey's work wasn't just about drawing borders. Along the way, they calculated the heights of major peaks in the Himalayas. In 1856, using triangulation, surveyor Radhanath Sikdar made the famous calculation that a peak then called Peak 15 was the highest mountain in the world, what we now call Mount Everest. And yes, they figured that out without ever setting foot on it, just angles, baselines, and relentless patience. The Great Trigonometrical Survey also revealed something fascinating about the Earth itself. It's not a perfect sphere. It's an oblate spheroid, slightly flattened at the poles and bulging at the equator, but the survey's measurements suggested the bulge wasn't perfectly symmetrical. This fed into debates among scientists back in Europe about the exact shape of our planet. Logistically, the project was a nightmare. It required a constant supply chain for equipment, food, and pay for the massive teams of workers. Local labourers, often hundreds at a time, carried chains, built observation towers, and cleared sight lines through forests. Sometimes they had to cut swaths several kilometers long, just to see from one point to the next. Weather could ruin months of work. A single season of heavy rains could make baselines impassable, wash away markers, and force teams to start over. And in some regions, political unrest or war would halt the survey for years at a time. Still, the work went on. Decade after decade, triangles marched across the map, from the southern tip of India to the Himalayas in the north, from the Bay of Bengal to the deserts of Rajasthan. Each new triangle locked into the next like pieces of a massive geometric puzzle. By the time the main work wrapped up in the late 19th century, the Great Trigonometrical Survey had covered an area of over 2 million square kilometers. It was one of the most ambitious scientific projects of its time, and its data influenced everything from geology to navigation. But there's a more complicated side to the story. The survey was a tool of empire, and the maps it produced weren't just for science, they were for control. They helped the British tax system operate with ruthless efficiency. They allowed for military planning down to the smallest details. The same precision that delighted scientists also strengthened colonial rule. Even so, from a purely mathematical and engineering perspective, the achievement was staggering. Imagine starting a project today with the goal of mapping an entire continent by hand, knowing you might not live to see it finished. That's the level of commitment these surveyors had. And it all hinged on triangulation, the quiet, stubborn method of turning angles into distances and distances into maps. From Lambton's first baseline in Madras to Everest's Himalayan calculations, the Great Trigonometrical Survey was a testament to what happens when geometry meets determination. So the next time you see Mount Everest on a map, remember that before climbers ever set foot on its slopes, a man with a theodolite and a lot of patience had already conquered it, with nothing more than math. If you ask a kid to draw the Earth, they'll probably make a nice blue circle. If you ask a cartographer or a mathematician, they'll sigh deeply, grab a coffee and say, well, it's complicated. The simple answer is the Earth is round. The more accurate answer is it's sort of round, but also squished, lumpy and a little bumpy in places, which makes it sound less like a majestic planet and more like a slightly overripe melon. Let's start with the basics. If Earth were a perfect sphere, mapping it would be a lot easier. But thanks to the magic of physics, spinning things don't stay perfectly spherical. The planet's rotation causes it to bulge at the equator and flatten at the poles. That gives us what scientists call an oblate spheroid. Think of it like a beach ball someone sat on gently. This bulge means the equator is about 43 kilometers farther from the center of the Earth than the poles are, which doesn't sound like much until you realize that for a surveyor, those kilometers matter. If you're trying to measure distances accurately over thousands of kilometers, you have to account for that bulge, or your maps start lying to you. In the 18th century, there was a fierce scientific debate over exactly how squished the Earth was. The French Academy of Sciences sent 2 expeditions to measure meridian arcs, one to Lapland near the Arctic Circle, the other to Peru near the equator. The idea was simple. If the Earth is flattened at the poles, a degree of latitude should be longer near the poles than near the equator. The expeditions were anything but simple. The Lapland team froze, the Peru team baked, and both teams battled illness, terrain, and the occasional political mess. But the results confirmed it. The Earth is indeed an oblate spheroid. Newton had been right all along. But wait, it gets messier. Even if you accept the bulging equator, the Earth's surface isn't smooth. Mountains, valleys, ocean trenches, and uneven distribution of mass all make the planet slightly irregular. This leads us to the concept of the geoid, the shape the Earth's surface would take if you smoothed out the continents and let the oceans flow freely under gravity alone. Picture a lumpy potato, and you're close. Scientists sometimes even call it the potato Earth. Not the most majestic nickname, but accurate. Why does any of this matter for mapping? Because if you're trying to pinpoint locations, launch satellites, or build bridges that actually meet in the middle, you need to know which Earth you're working with. The perfect sphere, great for simple math, the oblate spheroid, better for most global calculations, or the geoid, best for extreme precision. Surveyors in the age of triangulation had to choose a model for Earth's shape and stick with it. If their model was wrong, errors would build up as they extended their measurements. This is one reason why massive surveys like the French Meridian Project or the Great Trigonometrical Survey of India were so important. They didn't just make maps, they improved our understanding of the planet's geometry. Here's a fun twist. Because the Earth isn't perfectly uniform inside, gravity isn't the same everywhere. In some places you actually weigh a tiny bit more or less, depending on the density of the rock beneath you. This affects measurements too. In fact, during the Indian survey they found that mountains like the Himalayas messed with their plumb lines. Gravity pulled the surveying instruments slightly toward the mountains, throwing off the readings. They had to invent mathematical corrections to account for the mountain effect. All this complexity means that mapping the Earth is a constant balancing act between mathematical simplicity and physical reality. In the old days, you had to pick one model and live with its flaws. Today, with satellites, we can measure the geoid with incredible precision, tracking tiny changes in gravity and surface height over time. Of course, this doesn't change the fact that for most everyday purposes, calling Earth round works just fine. Airline pilots don't calculate flight paths based on the potato model, but for certain tasks, like aiming a missile, landing a rover on Mars, or building a tunnel between continents, those extra centimeters and degrees of curvature make all the difference. In the end, the complicated shape of the Earth is a perfect example of why mapping is both science and art. On paper, we like clean shapes and neat formulas. In reality, our planet is messy, uneven and full of quirks. But that's what makes mapping it so endlessly fascinating. So yes, the Earth is round, but not that round. And every cartographer, from ancient times to modern GPS engineers, has had to wrestle with that squished, lumpy truth. If you've ever tried wrapping a gift with paper that's too small, you know the frustration of trying to make something flat cover something round. Now imagine trying to flatten the entire planet onto a sheet of paper. That's what map projections are all about. And it's every cartographer's headache. The Earth is three-dimensional and curved. Paper is two-dimensional and flat. You can't go from one to the other without some kind of distortion. The trick is deciding what you're willing to distort. Shape, size, distance, direction, and how much you can get away with before people start yelling at you. Take the famous Mercator projection. Invented by Gerardus Mercator in 1569, it was a revolutionary tool for navigation because it preserved direction. On a Mercator map, a straight line represents a constant compass bearing, which is fantastic for sailors. The downside? It massively distorts size as you move away from the equator. That's why Greenland looks bigger than Africa on a Mercator map, even though Africa is about 14 times larger. Mercator didn't care about size accuracy. His audience was sailors plotting courses, not geography teachers hanging maps on classroom walls. But centuries later, when the Mercator projection became the default world map for everything, people started to notice the problem. Some argued it made Europe and North America look more important by inflating their apparent size while shrinking Africa and South America. Map politics were born. Then came the Gall-Peters projection, which preserves size but distorts shape. On a Gall-Peters map, countries are shown in their correct area, relative to each other, but they look stretched near the equator and squished near the poles. Supporters saw it as a fairer, more egalitarian map. Critics thought it looked weird and ugly. Basically, the Mercator versus Gall-Peters debate is the cartographic equivalent of arguing over which pizza topping is correct. Passionate, endless, and a little ridiculous. Of course, there are dozens of other projections, each with its own trade-offs. The Robinson projection tries to find a balance, distorting everything just a little bit so nothing is too wrong. The Winkle triple is another compromise, so beloved by the National Geographic Society that they adopted it as their standard in. And then there are specialty projections like the azimuthal equidistant, which shows all points at proportionally correct distances from a central point. Great if you want to plot airline routes. Less great if you care about accurate continent shapes. Some projections are purely for fun or artistic effect. There's the good Homoloucene, which looks like the world map has been cut into sections like an orange peel. There's the Dynaxion projection by Buckminster Fuller, which unfolds the globe into a series of triangles so that no landmass is split, and so that it looks like Earth exploded into a geometric puzzle. The point is, there's no such thing as a perfect flat map of the world. Every projection lies to you in some way. The question is, which lie do you prefer? Do you want accurate shapes but misleading sizes? Accurate sizes but distorted shapes? Equal distances in one direction but warped in another? For centuries, cartographers have wrestled with this. In the age of exploration, the focus was on navigation. Mercator ruled because sailors needed to get from point A to point B without accidentally visiting point C or sinking along the way. In the modern era, the focus shifts depending on the audience. Educators, scientists, governments, or artists. Even Google Maps cheats. On your screen, you're looking at something very close to a Mercator projection because it keeps street directions consistent, but zoom out to the whole globe, and it gradually shifts to a 3D sphere to avoid the most glaring distortions. It's a projection that changes as you use it, which would have blown 16th century cartographers' minds. Projection problems can also get weirdly political. In the 20th century, the United Nations adopted the azimuthal equidistant projection centered on the North Pole for its emblem. It's a neat choice visually, but it also means Antarctica looks like a giant white ring. A subtle reminder that, yes, the UN technically considers it part of the world too. Then there's the challenge of explaining to people that the map they grew up with isn't wrong, so much as it's serving a purpose. If you've only ever seen a Mercator map, the first time you see an equal area projection can feel like someone tilted the planet overnight. How did Africa get so big? Was it always like that? Yes. Yes. At the end of the day, map projections are a compromise between the reality of a round Earth and the convenience of a flat surface. They're a reminder that maps aren't the territory, they're interpretations. Just like a portrait can capture someone's smile but not their voice, a map can capture certain truths about the world, but not all of them at once. So the next time you look at a world map, ask yourself, what's this map lying to me about? The answer will depend on the projection, and that's where the real fun begins. For most of history, maps were made by people with their feet on the ground, squinting at distant hills through instruments and scribbling in notebooks. Then, in the 19th and 20th centuries, cartographers discovered a much better way to see the world. Go up. At first, going up meant balloons. The idea was simple. Float above the ground, take a look around, and sketch what you see. In 1858, a Frenchman named Gaspard Félix Tournachon, better known as Nadar, became the first person to take an aerial photograph. He leaned over the side of a hot air balloon with a camera the size of a microwave, pointed it at Paris, and snapped history's first bird's-eye photo. It was genius. From the air you could see roads, rivers, and building layouts without spending weeks trudging through them. Of course, the early technology had some drawbacks. Balloon rides were at the mercy of the wind, so you could end up mapping an area you had no intention of visiting. And the cameras weren't exactly point and click. They needed long exposures, which meant staying perfectly still in a swaying basket dozens of meters above the ground. Still, the idea caught on. By World War I, aerial photography had taken a massive leap. Literally, airplanes replaced balloons, giving cartographers speed, range, and altitude. Pilots flew with cameras mounted to the underside of their planes, snapping overlapping photos of the ground below. The overlap wasn't a mistake. It allowed for stereoscopic viewing, where two slightly different photos could be looked at through a special device to create a 3D effect. Suddenly, surveyors could measure the height of hills, buildings, and trees without leaving their desks. This was a game changer for both military and civilian mapping. Armies used aerial photos to plan troop movements, identify enemy positions, and create up-to-date battlefield maps. Civilians used them to update city plans, design new roads, and study land use. For the first time, maps could be updated quickly and with incredible accuracy. Then came photogrammetry, the science of making measurements from photographs. With the right math, you could take two or more images of the same area from different angles and calculate distances, heights, and even volumes. The old days of dragging chains across fields were officially numbered. Between the wars, aerial mapping spread to peacetime users. Forests were surveyed for timber resources. Farms were mapped for irrigation planning. Cities used aerial photos to plan expansions. You could now map a region in days that might have taken months or even years on foot. Of course, there were still quirks. Early aerial mappers had to deal with changing light conditions, camera jams, and the occasional bird deciding to photobomb the shot. And let's not forget the pilots, who had to fly in precise straight lines for hours while keeping a steady altitude. Not an easy feat in the bumpy air above mountains or deserts. By World War II, aerial mapping was a highly developed science. High-altitude reconnaissance planes could photograph huge swaths of land in a single flight. These maps weren't just for navigation. They were used for planning bombing raids, coordinating invasions, and even deceiving the enemy with fake information. After the war, much of that technology trickled into civilian life, leading to the creation of detailed topographic maps for entire countries. Then satellites arrived. In the 1960s, spacecraft like the American Corona series began taking photos from orbit. At first, the film had to be physically returned to Earth. The satellites would drop canisters from space, which were then caught mid-air by planes with giant nets. It sounds like something from a spy movie, but it worked, and it meant that maps could now cover the entire globe without setting foot or wing anywhere near the area. Today, aerial mapping is a mix of airplanes, drones, and satellites. High-resolution cameras can capture details down to a few centimeters. LiDAR, light detection and ranging, uses lasers to map terrain even through dense forests, revealing ancient structures hidden under jungle canopies, and everything is processed, thus powerful software that can stitch images together into seamless interactive map. The jump from a man in a balloon with a shaky camera to a satellite orbiting at thousands of kilometers an hour is staggering. But the principle hasn't changed. Get above the ground, take a picture, and let the math do the rest. And yes, while we now rely heavily on satellites, there's still something magical about the first time humans looked down from the sky and realized they could see and map an entire city in one glance. Aerial mapping didn't just make better maps, it changed the way we think about our world. From here on out, surveying would no longer mean walking every inch of the land. It could mean sitting in an office, coffee in hand, turning overlapping photos into a map so detailed you could spot your neighbor's clothesline. When the Cold War kicked in after World War II, maps went from being tools of exploration to weapons of information. Every road, bridge, factory, and coastline became potential military intelligence. Cartography wasn't just about knowing where you were anymore. It was about knowing exactly where the other guy was, preferably before he knew you were looking. The United States and the Soviet Union both poured staggering amounts of money into secret mapping projects. High-altitude reconnaissance planes like the U-2 flew over enemy territory, snapping ultra-detailed photographs. These images were often so sharp you could count the cars in a parking lot, assuming you didn't get shot down first, which is exactly what happened to U-2 pilot Francis Gary Powers over the Soviet Union. His capture caused a diplomatic nightmare, but it also made one thing clear: aerial reconnaissance was risky business. So both sides pushed for something safer: satellites. The Americans launched the Corona program in 1960, the first successful spy satellite system. The idea sounds like something out of a spy novel. The satellite took photographs on physical film, then dropped the film canisters back to Earth. Special recovery planes would literally catch the falling canisters in mid-air using hooks and nets. If they missed, the canisters had flotation devices, so ships could retrieve them. And yes, sometimes they landed in the ocean and had to be fished out before anyone else found them. The Soviets had their own equivalent programs, keeping their methods just as secret. Both sides raced to improve their imaging technology, producing maps of enemy territory so detailed that they could spot missile silos, submarine pens, and even individual aircraft parked on runways. These weren't maps for public use. They were top secret, classified higher than your grandmother's pie recipe. Possessing them without clearance could land you in serious trouble. Even the scale of these maps was often a military decision. Too much detail could reveal your own capabilities. But here's where it gets interesting. Both the US and the USSR also mapped huge parts of the rest of the world in incredible detail. The Soviets, in particular, created highly accurate maps of cities all over the globe, even ones deep inside NATO countries. Some of these maps were better than the local government's own. There are stories of Western companies in the 1990s using declassified Soviet maps because they were more accurate than the official ones. Meanwhile, the US used its satellite imagery to update global mapping databases that would later feed into civilian projects. In a way, the Cold War laid the groundwork for the modern era of Google Earth and GPS navigation, though no one would have guessed that at the time. Of course, this was also the era of deliberate misinformation. Just as cartographers had once put trap streets in maps to catch plagiarists, governments sometimes altered publicly available maps to hide sensitive facilities. Entire towns could be omitted, roads rerouted, and coastlines slightly shifted to throw off anyone trying to use civilian maps for military purposes. This secrecy led to some bizarre situations. Imagine being a tourist in the Soviet Union in the 1970s and finding that the official city map you bought didn't quite match reality. Streets might be missing, buildings might be relocated, and landmarks could be drawn slightly wrong. It wasn't bad cartography, it was intentional. Then there was the constant cat and mouse game of spotting new developments. Analysts would compare satellite images taken weeks apart, looking for tiny changes. A new building, a cleared patch of land, a shadow that hinted at something under construction. One famous case was the discovery of Soviet missile sites in Cuba in 1962, the trigger for the Cuban Missile Crisis, thanks to reconnaissance photographs. Those photos led to one of the tensest standoffs in history, all because of what could be seen from above. The Cold War also pushed the limits of mapping technology. The need for better resolution led to more advanced optics, faster film, and eventually digital imaging. Computers began to assist with analyzing photos, stitching them together, and creating highly accurate, up-to-date maps. And while the maps themselves were locked away in government vaults, the techniques developed during this time spilled over into civilian science. Remote sensing for agriculture, environmental monitoring, and disaster response all benefited from Cold War innovations. In an odd twist, the same tools built to track missile sites ended up helping farmers figure out when to plant corn. By the time the Cold War ended in the early 1990s, a lot of this material was declassified. Suddenly, the public got a glimpse of just how much the superpowers had been watching, and just how good they'd gotten at turning photos into maps. For historians and geographers, it was like opening a treasure chest. For the rest of us, it was a reminder that during those decades of political tension, even the humble map was part of the front line. Cold War cartography wasn't about pretty atlases or schoolroom globes. It was about information dominance, secrecy, and the belief that knowing your enemy's map better than they knew yours could be the difference between peace and disaster. Once upon a time, getting lost was a normal part of life. You'd take a wrong turn, wander down an unfamiliar road, and either stumble upon something interesting or spend an hour asking strangers for directions that made no sense. Then along came GPS, the technology that promised to make getting lost obsolete. And for the most part it did, though sometimes it just helps you get lost in new and exciting places. GPS, short for Global Positioning System, began as a US military project in the 1970s. The idea was to have a network of satellites orbiting Earth, constantly sending out precise time signals. If you had a receiver on the ground, you could pick up those signals, figure out how long they took to arrive, and use that to calculate your exact position. It's like cosmic triangulation, except instead of measuring angles from hilltops, you're measuring the travel time of radio signals from space. The first GPS satellites were launched in 1978, and by the mid-1990s the system was fully operational. For a long time though, civilians didn't get the same accuracy as the military. There was something called select availability, where the signal for non-military users was intentionally degraded. Your GPS might get you close to your location, but not close enough to guide a missile. In 2000, that restriction was lifted, and suddenly civilian GPS accuracy improved overnight from about 100 meters to about 10 meters. It was like turning on the high-definition version of reality. The basic math behind GPS is beautifully simple. Each satellite carries an atomic clock that keeps incredibly precise time. Your receiver also knows exactly where each satellite is supposed to be at any moment. When a satellite sends out a time-stamped signal, your receiver notes when it arrives. The time difference tells you how far away that satellite is. Do this with at least 4 satellites, and you can pinpoint your location in 3 dimensions: latitude, longitude, and altitude. Of course, making that work in the real world is anything but simple. You have to account for atmospheric delays, tiny variations in the satellite's orbits, and even the effects of Einstein's theory of relativity. Yes, time runs a little differently for satellites in space than for clocks on Earth. Without those corrections, GPS would drift off by kilometers in just a day. Once the accuracy improved, GPS quickly moved from military use to just about everything else. Ships, planes, and cars all adopted it for navigation. Hikers carried handheld GPS units into the wilderness. Farmers used it to guide tractors with centimeter-level precision, planting crops in perfectly straight lines. Surveyors found they could measure distances and positions faster than ever. And then came smartphones. Suddenly, GPS wasn't just for navigation, it became part of everyday life. You could open a map app and see exactly where you were, get turn-by-turn directions, track your morning jog, or check which restaurants were nearby. Taxi and delivery services were transformed. No more circling the block for 15 minutes looking for an address. Of course, GPS also has its quirks. Sometimes it's a little too confident. Who hasn't heard a navigation app say turn left, only to find that left leads directly into a lake or a cornfield? There are stories of truck drivers following GPS instructions straight onto roads too narrow for their vehicles, or into dead ends in remote areas. It turns out that while GPS knows where you are, it's only as smart as the map it's connected to. GPS has also changed the way we think about privacy. When your phone is constantly broadcasting its location, that data can be used for good, like finding your lost phone, or for more questionable purposes, like targeted ads that pop up when you walk past a store. It's a reminder that the same tool that can help you find your way can also be used to keep track of where you've been. Despite the quirks, GPS has become so ingrained in our lives that it's easy to forget how revolutionary it really is. The idea that you can stand anywhere on Earth, hold a small device in your hand, and know your position within a few meters, instantly, would have sounded like magic to the surveyors and explorers of the past. And here's the kicker: GPS isn't the only game in town. Other countries have built their own systems, like Russia's GLONASS, Europe's Galileo, and China's Beidou. Many modern devices can use signals from multiple systems at once, improving accuracy even further. So yes, GPS has mostly killed the art of getting lost. But it's also given us a strange new relationship with the world. We no longer have to memorize routes, carry paper maps, or ask for directions from that one guy in the village who insists you just keep going past the old oak tree, even though it was cut down 20 years ago. Instead, we trust a calm robotic voice to guide us, sometimes into traffic jams, sometimes onto questionable shortcuts, and occasionally into very wrong turns. But even when it messes up, GPS has fundamentally changed how we navigate, how we plan, and how we understand our place on the planet. It's the ultimate end point in a story that began with people counting steps and marking trails in the sand. Now, the entire history of mapping fits in your pocket, and it talks to you. If there's one thing humans are really good at, besides inventing snacks, it's measuring things. We measure our height, our weight, our speed, our distance from the moon, even how long it takes to boil the perfect egg. If it exists, we want a number for it. This obsession goes way back. The earliest humans measured by comparing to themselves, a handspan, a foot, a stride. That worked fine for small-scale life, building huts, trading fish, or deciding who threw the spear the farthest. But once we started trading with strangers, those units became a problem. One person's foot wasn't the same as another's. You could see how this might cause arguments, especially if you were buying expensive cloth by the yard and the seller's yardstick was suspiciously short. So, we tried to standardize. Ancient civilizations came up with official units: the Egyptian cubit, the Roman mile, the Chinese li, but each empire had its own definitions, and often several competing versions. By the Middle Ages, Europe was a patchwork of measurement chaos. Different towns might have completely different ideas of how long a mile was. It was the kind of mess that made map-making interesting. Why do we do this? Partly because numbers make the world feel more manageable. If you can measure it, you can compare it, replicate it, and control it. Measurements are the bridge between the physical world and human understanding. They let us turn far into 12 kilometers and pretty tall into 1.85 meters. And measurement doesn't stop at the obvious. We've measured the depth of the oceans, the speed of light, the mass of the Higgs boson. We measure things so small that we have to invent new math to describe them, and things so large that they're expressed in light years, the distance light travels in a year. We even measure time itself so precisely that we can detect differences in how fast it passes at different altitudes. Yes, your watch actually ticks a tiny bit faster on top of a mountain than at sea level. Mapping is just one branch of this obsession, but it's a perfect example of how far we'll go to get the numbers right. We've dragged chains across continents, climbed mountains with theodolites, sent balloons and planes into the sky, launched satellites into orbit, and bounced lasers off the moon, all in the name of knowing exactly where things are. Of course, measuring the world isn't just a practical exercise, it's also deeply human. There's something satisfying about pinning down the unknown. It's the same impulse that drives people to time their morning run or weigh their homemade bread. Measurement turns the messy, unpredictable world into something we can write in a notebook, or these days into an app. There's also a certain irony in our obsession. The more precisely we measure, the more we realize how messy reality is. The Earth isn't a perfect sphere. Gravity isn't perfectly uniform. Even the length of a day isn't exactly 24 hours. It changes by milliseconds thanks to tidal forces, earthquakes, and other factors. Perfection is an illusion, but that doesn't stop us from chasing it, and measuring has its cultural side effects. It changes how we think. Once you have a system of units, you start comparing things in those units. Tallest building, longest bridge, deepest canyon. You start competing to break records, whether it's fastest marathon or largest pizza. Measurement fuels curiosity, competition, and sometimes a little bit of absurdity. Without measurement, science as we know it wouldn't exist. Neither would engineering, navigation, or even cooking beyond a pinch of this and a handful of that. Every skyscraper, every airplane, every smartphone depends on thousands of measurements working together in perfect harmony. In a way, our obsession with measuring is also an obsession with knowing. Each number we write down is a little victory against uncertainty. It says, here is something we understand well enough to put into digits. Even if tomorrow we measure it again and get a slightly different number, we're still closer than we were yesterday. And that's the thread that runs from ancient rope stretchers on the Nile to GPS satellites in orbit. A refusal to leave the world unmeasured. Whether we're mapping continents or timing a 100-meter sprint, we're doing the same thing, trying to make sense of where we are, what we have, and how it compares to everything else. So maybe it's not surprising that maps, those beautiful distilled packages of measurement, hold such a special place in our history. They're the ultimate expression of the human urge to measure, a way to take the vast, complicated, three-dimensional chaos of the world and put it into a form we can fold up, stick in our pocket, and say, I understand this. Of course, we'll never finish measuring. There will always be new depths to plumb, new distances to clock, new records to beat, and that's fine. It's not really about reaching the end, it's about the process, the joy of turning somewhere out there into a precise coordinate. The truth is, humans will probably be measuring things until the end of time, and when time itself ends, we'll probably try to measure how long that took. Close your eyes for a moment and picture a map, not the one on your phone, not the glossy one you saw in school, just the one that lives in your head. It's probably a little messy. Maybe it's full of places you know well, your hometown, the route to work, the coastline you've driven along on vacation. Maybe there are big blank spaces where you've never been, filled in with vague guesses. And that's fine, because every mental map is a personal version of the world. Long before we had atlases or satellites, this was the only kind of map humans had, the one we carried in our minds. Traders memorized the bends in a river, sailors remembered the way the stars looked before dawn, and hunters kept track of where the herds usually passed. These mental maps weren't always precise, but they were enough to get home, enough to find food, enough to pass knowledge to the next person. Now we live in a world where the official map is always a tap away. We can zoom from a street corner to a whole continent in seconds, but the map in your head still matters. It's the one that tells you how to get from your kitchen to the fridge at 2 a.m. without turning on a light. It's the one that remembers that shortcut through the park. It's the one that holds the invisible connections, the way a place feels, the memories attached to it, the stories that give it meaning. When we've spent this whole journey talking about measuring and mapping, it's easy to think of maps as only lines and coordinates. But every map is also a story. The Babylonian clay tablets told a story of a small, familiar world. The medieval mapper Mundi told a story of a world shaped by faith. The explorers' maps told a story of adventure and curiosity. The great trigonometrical survey told a story of ambition and precision. And your mental map, it tells your story. Cartographers throughout history have tried to capture the world, but even the best map is just a version of reality frozen in time. The rivers might change course, the roads might disappear, new cities might spring up where there was once nothing but grass. But the human desire to draw the world, to say here's where we are and here's how everything fits together, never changes. We've measured the Earth with sticks and shadows, with triangles and chains, with balloons, planes and satellites. We've flattened it onto paper and wrapped it back into globes. We've argued about projections and units, about what should be at the center and what should be left out. And through all that, we've carried our own private maps inside us. Maybe that's why maps feel a little magical. They're more than just tools. They're a way of taking something vast and unknowable and making it small enough to hold in your hands. They're proof that we can look at the chaos around us and find patterns. They're a reminder that even when we don't know exactly where we're going, we can still try to chart a course. And so, as we come to the end of this story about the people who measured the world, I like to think that they weren't just making maps for kings, empires, or armies. They were also making them for people like us, curious, wondering, occasionally lost, always looking for our place in the bigger picture. The next time you see a map, take a moment to imagine the hands that made it. The surveyor squinting through a theodolite in the heat. The cartographer bent over a desk, inking a coastline. The pilot circling high above with a camera. The programmer turning satellite data into pixels, and behind all of them thousands of years of people trying to figure out exactly where they stood on this strange spinning planet. And if, in the quiet of the night, you close your eyes and picture the Earth, the curves of the continents, the sweep of the oceans, the little dot where you are, then you're doing the same thing humans have done since the very beginning, drawing the world in your mind. Not bad for something we started with. Nothing but footsteps and a good guess.